Okay, now there's a few different ways to do this one. We're given a particle with a mass of 1 kilogram and we're told that it's accelerated from rest. So the initial speed is equal to 0. The final speed is equal to 0.800 c, and it does this in a period of 60 seconds. And we're asked what's the average force. So the average force is just the total force, which is so to calculate the average force, we can just assume that there's a constant force acting on this particle to get it up to this speed in this time interval. So we know that force is equal to dp dt. So we can write this as F dt is equal to dp, and then we can integrate both sides. Now for the time, this side's integrated in terms of time, we have 60 seconds. So we're going from time equals 0 up to 60 seconds. With this side, we're integrating in terms of momentum. So we're going from the initial momentum to the final momentum. Now the initial speed is 0, so the initial momentum is going to be 0 because momentum is given by mv over the square root of 1 minus v squared on c squared, which is 0 when v is 0. Now we'll need to work out the final momentum, so P final is going to be equal to m, which we're told is 1, times the final speed, which is 0.800 c, over the square root of 1 minus 0.800. Now this is squared, and then we've got c squared over c squared. And as always, this c squared will cancel this c squared. And so to calculate this, we've got 0.800 c over the square root. Now we've got 1 minus 0.8 squared, which is 1 minus 0.64 squared, which is 0.36. And when we take the square root of that, we end up with 0.6. So that's 0.800 c divided by 0.6. And so that is equal to 1.33 c. This will be in kilogram meters per second. The meters per second are contained within the c here. We could, if we wanted at this point, substitute in 3 times 10 to the 8 meters per second for this c here. Okay, so integrating this, when we integrate force, we're assuming it's a constant force because we've been asked to calculate the average, so it doesn't vary with time. So this is a nice easy integral. This is equal to ft from 0 to 60, and this one is equal to p, and that's evaluated at p initial, which is 0, and p final, which is 1.33 c, or we can substitute in the 3 times 10 to the 8 there if we want. Okay, so this is equal to f times 60. When we do f times 0, we just end up with 0, is equal to 1.33 times c. And so the average force is equal to 1.33 times c over 60, which, when we solve it on the calculator, is equal to 6.67 times 10 to the 6 newtons. Now the mass was only given to 2 significant figures, so technically we should really write this as 6.7 times 10 to the 6 newtons. Now, an interesting thing we could do is, well, what happens if we apply this force for 60 seconds in the non-relativistic case? Just as a little extension. In that case, we've got F is equal to ma, and since it's just 1 kilogram, we know that the acceleration will be equal to the force, which is equal to 6.7 times 10 to the 6 meters per second. And then if we worked out, well, how fast would it be going if it accelerated at this rate for 60 seconds, we can use our kinematic equation here, and this u, the initial speed, was 0. So that would be equal to 6.7 times 10 to the 6 times 60, which gives us 4 times 10 to the 8 meters per second. So you can see, without accounting for relativity, if we applied this force for 60 seconds, we'd end up with a particle which was going faster than the speed of light, which we know is impossible.